Okay, hello everyone. My name is Youness. I was a student at BCIT and working on material properties, hydrothermal material properties, basically measurement those properties. So first of all, thank you for inviting me for this event. I am pleased to present for you and for the community of building science at the BCIT and all in a broader perspective as well. So I was working on measurement and measuring different hydrothermal properties and building materials at different temperature and relative humidities. Basically, we were working on temperature dependency, as we knew, and based on the relative, based on the literature reviews, we understood that these properties are affected by the temperature fluctuations. So I'm gonna go over the whole content. I just want to go fast through the presentation, as I have many slides. So I'm gonna cover the start from problem statement, literature review, then building materials, the list of them, and the experimental procedure and the result and discussions. So I'm going to start from a problem statement. We as Afshin started with his project, almost all of the simulation modeling software and tools, they use building properties, material properties for as a database for the simulation. And this is going to be one of the most important parts of their database. So it's really important to have a very updated set of properties to be used for those simulation and to get meaningful results, like what Afshin did from the whole process and using those tools. So this is important to have a very updated set of properties, but we know that these properties, based on the literature review and the actual result in reality, we know that these are affected by temperature, and this happening while in some regions like North America, these materials and building envelopes in general are exposing to different temperatures through the year, which some of them are really extreme, similar to Canada, and this is reality. While in the lab, we always, as standards recommends, we always measure the properties only under the limited range of temperature and relative humidities. There are few and some other labs that they do frequently measuring different material at different temperatures, but they are not systematic, and there are no full and complete set of these material properties. Besides of these, materials are continuously evolving in terms of the manufacturing process and also in development of the material itself. So it's really critical to determine a very updated properties to be used in our simulation models. So for this study, I went through the theories and mechanisms. Started with the heat and moisture transport theories through the material, the porous materials, and then measuring different properties based on the standards available standard, and go through the temperature dependency and see the result of that. The materials that I was measuring were thermal conductivity, specific heat capacity, absorption, isotherm, water vapor permeability, and water absorption coefficient. So I'm going to through each of those quickly to that what are they. So I started with like basics properties like density and porosity of the material. I later explain how I did it. For the thermal conductivity, of course, we use all the available knowledge and principles and equation for measuring thermal conductivity. And for the moisture transport, we know that we are talking about water here. So we have three phases of water in the material in reality, as a shape of solid, which is ice, liquid, and gas, which is vapor, that affect the material and when go through the pores of the material. So when the relative humidity goes high, similar to a place like Vancouver, so the concentration of vapor molecules just goes high, and it causes to absorb as a layers to the surfaces of the pores of the material, and it goes high and higher and higher and more layers, and start to be like in liquid phases, which after that as associated with the moisture transfer through the material. So when we measure this amount of the vapor and concentrated moisture vapor as moisture in the material pores, and when we plot it against the relative humidity, we call it absorption isotherm. So we can have absorption isotherm of the material at a certain temperature. Then again, we calculated these properties as subtracting the dry weight of the material from the like moisture material. So after that, for vapor permeability, we used cup method, dry cup and wet cup. These are explained in ASTM standards, that we can measure the vapor flow through the material and the concentration and the intensity of that. And the process is way complicated compared to the absorption isotherm. And you need to consider several items, the air pressure, the vapor pressure, the buoyancy, even the measuring and weighing the material itself. So it was a very sophisticated procedure among the others. After that, for measuring the liquid transport through the material, we used the partial immersion, immersing the material into water. So the material was in contact with the surface of the water and started started the capillary flow and absorbing water from the below, and of course it goes again through different phases until it reaches the top of the building material. We use this method. This is the schematic shape of that, and of course it has its own measurement method, which is basically the rate of absorbing water intake against the time. So for the materials, we try to have and collect as many as material along the envelope at different layers and different families of the materials. So we went through selecting few materials on each categories, like cladding, sheathing boards, building wraps, framing. Here it's wood stud, and different installations. So in total, we selected 17 different materials. So we started buying them, of course, and transport them to the lab and start cutting based on the nature of the test that we had according to the ASTM standard available, and manage them and let them dry and like conditioned in a lab environment. But obviously we didn't want to test them all in lab conditions. So this is the first step to just get them, because some of them were like dry, getting them from outside, like get from the market, and from they were like soaking wet in the wood. So after that, we did condition them based on our tests and our proposed temperature and relative humidity before the test, and we went through the test. So in total, we had planned to perform 537 different tests. That was a big plan, and we went through almost all of them, and completed exactly 537 tests, which took actually a long time. So these are the list of materials and the properties that you see at different relative humidities and temperatures. So we had them to be tested in 3 relative humidities, 50, 70, and 90%, and 3 different temperatures, 3 degree centigrade, 21, and 45 for the moisture performance. For the thermal performance, actually, we went through 5 or 6 temperatures, started from 5 to 60. So for the material preparation and test procedures, we started with thermal conductivity. We followed for almost all of the, actually for all of the properties, we used ASTM for North America standard, and ISO, the European, or maybe the like universal version of it. So we combined those, and at the end of the day, for our project, actually, we extended the conditions to lower temperature and higher temperature, and see if that like procedure and method is applicable and is practical to do that. So we had to change those, we somehow had to develop our method to make it possible to do those measurements. So whatever we could buy from the market, we bought them, the material, and the rest of them, like this one, we made them. We asked contractors to make those for us, and like apply in place here in BCIT. So we asked the contractors to create like cellulose fiber insulation, and the previous one was the open cell spray foam, and I created the stucco based on the concrete mixture which we provided from the stores, from in this case from Home Depot. So we use the heat flow meter method, and using those heat flow meter apparatus in at BCIT material lab, and all the heat capacity and thermal conductivity were done using these 2 methods and 2 equipment. For the absorption isotherm, we used again another set of standards, and we prepared different size of the material, which most of them actually were 50 by 50 millimeters, and we did some preparation, like cutting through the insulation to get more vapor during the process and fasten the process. Otherwise, it took like 3 months. For the sorption isotope and the vapor permeability, actually, we use different climate, the combination of 3 temperature and 3 relative humidities. We had 9 conditions. We provide them with these climatic chambers at BCIT. And since some of these measurements are really sensitive, so and we are talking about really smart portion of vapor absorption, so it was critical to put them in a container while we do the measurement, like weighing the material, and also for eliminating all the fluctuation through the air conditioning through the lab. We use this bucket, as you see, like a transparent bucket for the weighing procedure. For the density of the material, for the dry density, actually we dry them in the oven. Again, following procedures from the standard, and for the saturated moisture content, we also followed, I think, the ASTM 1498 somehow. Yeah, 1498 ASTM standard, and it recommends that if you keep materials for more than 7 days under the column of water of like 10 centimeters at least, you can get water saturation or almost similar to that. You can do that with like a pressurized chamber, which with certain amount of Newton. So you can do that quickly, but we, based on the equipment, we did this procedure. And this is important for the end of the sorption and completing the sorption isotherm of each material. For the vapor permeability, we again cut, because we were using like the cup method, so we started to cut all material with the size of the mouth of the cup. And we prepared them all, and we start to attach those materials to the cup. We use the traditional way, which is the most effective current available way to do that. There are some other improvement and development, but they are not costly, and they need lots of time and effort to make those modified cups. So we use this one. We use the top one for the materials such as cellulose fiber, and we attach it to the cup. But since we tested at different temperatures, like lower and higher, you can see at the top one that lower temperature started to make the wax, which we use for the attaching and sealing the material to the cup, started to make that very brittle. And after like a few days before getting any meaningful result, we got like cracks, and of course it wasn't sealed anymore. So for the higher temperature also, we got like vapor migrating through the sealant, as you can see. So it wasn't sealed anymore because it was really soft. So we had to change those. These are like changing extensions and improving the methods that are available at like standards. So we, I went through different type of waxes with different melting points, and came up with different solutions for different temperatures. Again, we did like precautions for and very carefully for the weighing, measuring the material, the properties. And for the water absorption, similar to the other, we used two standards. So we cut, of course, following the procedure of the size of the material, we use 10 by 10 centimeters. The material shape, we cut all those and we create stucco.
Just want to make sure that you have like 2-3 minutes left.
For 15 minutes or for 20?
No, you have like 2-3 minutes.
Okay. Okay, so so we went through for absorption in particular, we went through improving our method and our equipment to test these tests on the chambers. And of course, the results we got, almost all of them were according and with a good agreement with the literature review with a few discrepancy differences. So thermal conductivity, basically, this is a sample for fiber cement. So thermal conductivity and specific heat capacity, they increase with the temperature. Some of them linearly, and some of them, like for the insulations, they increased like not linearly. So and this is the comparison of all the materials. So you can see that the insulations basically have the lower conductivity compared to something like a stucco, which was the most conductive material to heat. And for the absorption isotherm, that's the rule of thumb that the absorption it goes high by the relative humidity, but it decreases when the temperature increases, as the molecules they can't attach easily to the material pores, and also at lower temperature actually they start condensation, so they get like more moisture content at lower temperature. This is the comparison between all materials that we got. So cellulose, actually, we got the highest moisture content through the whole through all three temperatures, followed by wood material and also cladding material like cement based. So for water vapor permeability, this is a sample for the stucco, which increased again by the actually increased by temperature, and this is the normal graph for the vapor permeability. And here you can see the transmission rate. This is the flux, the vapor flux through the material. Again, cellulose is the highest one, followed by the building papers, which is common sense that those building paper are vapor open. So, and this is a vapor permeability. Again, the permeability of buildings paper are the highest among the rest of the materials. And for water absorption coefficient, with interestingly, the water absorption coefficient, the water uptake, when it goes to the contact to the water, it increased with the temperature. We got like faster water uptake, and it decreased actually with the relative humidity. This is the comparison between all of those. So cellulose fiber, actually, again, we got a highest rate for water absorption when it contacts to the water. And that was all the project. Thank you.